Hi, I'm Ashleya. Hello, currently writing about from evolutionary engineering college.
Hi, I'm Darshini, final year IT department from Evolutionary Engineering College.
Hi, I'm Deepashri BK, final year IT department from Emotional Engineering College, Vegas.
Hi everyone, as Aishwarya Tangam, Deepashri and Darshini have collaborated on a project titled A Hybrid Deep Learning Model for Detecting Fancy and Arbitrarily Shaped Text under the guidance of Mrs. N. Malathi, Assistant Professor, Department of Information and Technology from Evolutionary Engineering College. So let's get into our project. Text detection and extraction have become essential tools in today's digital age. From recognizing text on images to extracting data from documents, these technologies are revolutionary the ways we interact with information. Scene text detection and recognition have been the subject of in-depth research in recent years. Despite the advances, efficient and accurate end-to-end text spotting with arbitrary shapes remains challenging. End-to-end text detection and identification can be extremely helpful in many different fields, including healthcare, finance, law, and many others, where there is a requirement to handle enormous amounts of text rapidly and accurately. In this paper, we provide an end-to-end text spotting system that can efficiently locate and identify text in natural settings of various shapes. Proceeding with aim, our aim is to create a reliable and effective end-to-end spotting system for identifying text with arbitrary shapes and images, even when the text is curved or oriented in different directions. The system is built to locate text instances and identify their contents, as well as to recognize small texts that are difficult to read with naked eye. Following our objectives, our objective is to create a text spotting system that can recognize and identify text in photos that is arbitrarily shaped and fancy, and to add a cutting-edge hybrid deep learning model to the system to enhance performance and help better separate text from the other image elements. So proceeding on with the block diagram, here comes the visual representation of a block diagram on the following slide. This first step of an image is passed as an input which is taken from the data set CTW 1500. The CTW 1500 dataset consists of 1500 images, out of which 1500 images, 750 is used for training and the remaining 750 is used for texting. So first we will be pre-processing this data to remove noise content, and the next is followed by the lightweight backbone ResNet 50. The ResNet 50 model is added because to increase the accuracy. A network with 50 layers was designed to address the problem of diminishing gradients in very deep networks. This is the first model in our project. The architecture is based on enduring learning, where the network is constructed to learn enduring functions with respect to the layer inputs rather than trying to learn the needed underlying mapping indirectly. Also, this REST architecture is composed of several blocks, and the blocks also use skip connections that pass around one or more layers, allowing the data to flow through the network more easily. Coming with the next model, that is channel reduction. Here we reduce the channel number on feature maps to 128 via 101 cross 1 convolutions and obtain a feature pyramid. Then this feature pyramid is enhanced using FPM model, that is feature pyramid enhancement model, which is the third module. This is a type of network commonly used in computer vision tasks such as object identification and semantic segmentation. The main purpose of this network is to enhance the characteristic maps of a previous network, capturing multiple information from the input pictures. It scales at different intentions, and it typically consists of two key components: a characteristic pyramid network and a characteristic integration network, followed by the upsampling. Here we upsample the image which is extracted from the feature pyramid enhancement module. It is usually used to augment a specific area of a picture and to delete the low resolution picture on a big frame. We super sample and join the characteristic maps of characteristic feature pyramid, and it predicts the word areas. Then moving with the word spotting, here word spotting consists of text kernels and instant vectors, and this module consists of the output of text regions which is a result of this model. Although the text kernels lose the full shape of text, they can readily distinguish adjacent text instance. So as a result, instant vectors can point text regions at an appropriate text level, effectively combining the benefits of text regions and text kernels. Here we have used a hybrid deep learning model, that is EAST and REST 50. So EAST, it has two stages, and it quick and precise and scene text detection technique. It produces pixel-based word or text line predictions directly using a full conventional layer. So One potential approach we have used is combining the ResNet 50 with the East algorithm in order to identify word regions in natural pictures. ResNet 50 is a widely used deep learning prototype known for its impressive working in tasks like picture classification. So by joining these two techniques, it is possible to increase the strength of both the word spotting and in detection and extraction in natural images expressively. So after detection, and we are using a tesseract to extract the text exactly from the images. This is achieved through the ability of the network to learn complicated characteristics from pictures, allowing it to handle variations in fonts, sizes, and orientation of words. Next, we have a last module, that is audio conversion output module. We additionally added another module by converting the extracted text to voice by using a TTS module. So this model gives the extracted text as an output, as an audio a generated output, which can be used to real life applications where people can hear the output through audio. And here comes the output feature models which we have implemented. First is feature map generation. We can see that grayscale have been applied to each feature maps, and the channel detection of 128 size. We can see the difference between the upsampling and before upsampling module, which shows the difference in height and width. Next, followed by instance vectors, followed by the bounding box, which is a text detection module. Here it have detected the text even though it is in a different orientation with different fonts, and the extracted text have been displayed. And the result.mp3 is the output audio, which contains the extracted text as an audio converted output. Here comes the comparisons with other models. Let us have compared with our model, that is East plus S50, with other models, and we have achieved accuracy of about 90.5 percentage. Then the code implementation, that is we have implemented a code in Python programming in Google Colab platform. Followed by the conclusion, that is on the CTW 1500 dataset, the text detection and identification results from the combination of less than 50 and E's are really promising. The field of scene word spotting and identification can be advanced significantly with the help of the integrated ResNet 50 and East model. This model also demonstrates ability when processing text instances with various orientation styles, making it prepared for real world scene word spotting and different tasks. So next, followed by the feature work, the model demonstrates robustness when dealing with text instances that contains both Chinese and English characters, but not with other languages. Since we didn't train with the other language datasets, we can overcome this by training with more number of datasets with other language. And another area of research could be incorporation of prior knowledge on domain specific knowledge to improve the accuracy, and we also want to focus on increasing the strengthening its resistance to complicated sceneries and difficult lightning circumstances, as well as investigating its applicability to additional jobs like document analysis and optical character recognition. So when it comes to social impact, we can also use this in the real life applications for visually impaired people. This will be really such a great application if we have implemented as a real life. So people with visually impaired can use this tool to detect the text in natural scenes, as well as even normal people who have difficulties in reading fancy fonts and small text can also use this model to detect the text. So that's the end of our work. Thank you.